If you take a piece of wood, right, and put it on a workbench, you have to clamp it down before you cut it. I mean, it is just the most basic, fundamental rule of building anything. You secure the workpiece.
Oh, absolutely. Rule number one.
Right. But like the clamp you choose completely dictates whether that piece of wood turns into, a masterpiece or just a splintered disaster flying across the room.
Exactly. Because the clamp isn't just holding the material. It's actively absorbing the kinetic energy of the tool.
Yeah.
And if you scale that up from a simple wooden workbench to a massive high-speed industrial vertical machining center, the VMC, the stakes shift entirely. I mean, we're not talking about a few splinters anymore.
We're talking hundreds of thousands of dollars in ruined equipment.
And lost production, yeah. It's catastrophic.
Well, welcome to today's Deep Dive, everyone. We've got a massive stack of sources today. Engineering manuals, manufacturer specifications, and decades of maintenance logs.
That's a lot of reading.
It is. And our mission is to sort of synthesize all of this to understand this high-stakes, microscopic battleground of industrial manufacturing. Specifically, we are exploring the fourth-axis rotary table on a VMC and the really intense engineering trade-offs required to keep that table perfectly, immovably still.
Which is such a fascinating structural problem. Because, a fourth-axis rotary table is often misunderstood simply as a positioning unit.
Like just a motor that spins apart around, right?
Exactly, just something to expose a new side to the spindle.
Yeah.
But the moment the cutting tool actually touches the metal, that table ceases to be just a motor. It becomes a critical part of the machine's rigidity chain.
Okay, let's unpack this concept of the rigidity chain because it's central to everything we're exploring today. From what I'm gathering in the engineering specs, this means that during a cut, the spindle, the tool, the workpiece, the table, and the cast iron base all have to act as a single unbroken block of solid metal.
Right.
So any weak link in that chain it destroys the operation.
That is the exact definition, yeah. If the rotary table cannot hold its position against the violent forces of, say, a carbide cutter plowing through metal,
Yeah.
you break that rigidity chain.
And choosing the wrong clamping method for that table leads to severe chatter, indexing drift.
Accuracy.
Right. And in the worst cases, totally destroyed internal mechanics. Which brings us to our two contenders today.
The main event.
Exactly. On one side, we have pneumatic locking, which relies on compressed air. On the other side, we have hydraulic clamping, which uses oil. What we're doing today is, well, it's really a masterclass in engineering trade-off.
It really is. It's about choosing the right tool for the job based on force, speed, and maintenance.
And honestly, that's a framework you can apply to almost any system in life. You rarely get to have maximum speed, maximum force, and zero maintenance all at the same time.
Never. You are always forced to choose your priorities based on the reality of your specific workload.
So let's start with the quick and light option, the pneumatic approach. Going through the manufacturer specs, this seems to be the most common method for fast, everyday jobs.
Yeah, it's ubiquitous.
We're talking about systems that run on shop-supplied compressed air, usually needing a stable pressure range of like 5 to 8 bar.
Right, and that 5 to 8 bar range is standard across most facilities. Pneumatic locking is perfectly suited for what the industry calls 3+1 fixed position machining.
Okay, I'm looking at the diagrams for 3+1 machining, and I just want to make sure I'm visualizing the workflow correctly.
Sure, go ahead.
So the VMC is moving the cutting tool around in 3 spatial dimensions, X, Y, and Z. The fourth axis is our rotary table holding the raw material. In this 3+1 setup, the table rotates the part to a specific angle, say 90 degrees, and then locks into place with a burst of compressed air.
Right, it stops moving entirely.
The cutting tool machines that face, the table unlocks, rotates to the next angle, locks again, and repeats.
Exactly. The fourth axis isn't spinning while the tool is actually cutting.
Got it.
That's the crucial distinction. It's indexing to a spot and bracing itself. And the sources point out this pneumatic method is ideal for materials like aluminum, especially those 3C aluminum parts used in consumer electronics.
No, like phone cases and stuff?
Exactly. As well as copper, plastics, and smaller steel parts, like valve bodies.
And the cutting processes recommended for this setup are really specific. The manuals highlight multi-phase drilling, tapping threads, chamfering edges, and light end milling.
Yeah, those are the sweet spots.
I'm trying to figure out why air is perfectly fine for these, but, discourage for other cuts. And it seems to come down to the physical direction of the cutting force. Like when you drill a hole, the force of the drill is pushing straight down along the tool's axis directly into the bulk of the machine.
That downward force is called an axial load. And because the drill is pushing straight down, it isn't applying a rotational torque to the workpiece.
It's not trying to spin it.
Right. It isn't trying to spin the rotary table out of its locked position. So the required clamping torque to resist a drill pushing straight down is relatively low. It typically stays below 50 to 60 Newton meters.
And the table itself provides some mechanical resistance too, right? I mean, the pneumatic air pressure is usually paired with internal high rigidity structures.
Yes. The manuals mention things like roller cams or multi-disc brakes.
Right, I saw that. Roller cams use a series of bearings squeezed together to prevent rotation.
And multi-disc brakes use alternating plates of friction material pushed together by the air pressure.
Makes sense.
When you combine that mechanical friction with a purely downward cutting force, pneumatic locking holds its position beautifully.
But there is a massive catch.
Oh,
I want to try an analogy here. Is pneumatic locking like holding a piece of wood with a quick grip hand clamp?
okay, I like where this is going.
Like, you know, the plastic ones with the trigger? If I'm doing some light sanding or drilling a small hole, that clamp is amazing because it's incredibly fast and easy. But I wouldn't use a quick grip clamp to hold a log that I'm about to hit with a chainsaw.
That is perfect. That captures the fundamental limitation of the medium entirely. Because the medium here is air. And physics tells us that air, as a gas, is inherently compressible.
Right.
The molecules have vast amounts of empty space between them.
So no matter how much you pressurize that air inside the cylinder, it will always have a little bit of squish to it.
It acts almost like a very stiff spring. So the locking field is inherently less rigid than a solid fluid. If you expose that airlock table to high lateral forces...
Like a chainsaw.
Exactly. Imagine spiral groove milling, where the tool is plowing horizontally and pushing hard against the side of the part. Or imagine hitting the part with heavy intermittent impact loads.
The air just can't take it.
Under that kind of side loading, the compressed air will physically yield. It will compress slightly within the chamber.
The rigidity chain breaks.
Yes. The table microscopically shifts. And when the table shifts under a cutting tool, you experience chatter.
Oh man, the sources mention chatter constantly, usually in the context of it being a total nightmare for machinists.
Oh, it is. Because chatter isn't just a bad noise. It's a self-sustaining acoustic vibration that physically destroys your operation.
Wow.
The cutting tool bites into the metal, the table yields backward because the air compresses, the tool snaps forward as the pressure equalizes, and it bites too deep. It flexes, releases, and bites again, hundreds of times a second.
That sounds incredibly destructive.
It work hardens the material you are trying to cut, it shatters expensive carbide inserts, and it leaves your finished part looking like it has tiny ripples carved all over it.
Yikes.
This is also why pneumatic locks fail at continuous four-axis interpolation, where the table is slowly turning while the cutter is heavily milling.
Because it's a dynamic side load.
Right. A pneumatic lock just isn't designed to secure those shifting dynamic forces.
Okay, so building right off that chainsaw analogy, if air is compressible like a spring and it fails under heavy side loads, what happens when we need to cut something totally unforgiving?
You need a different approach.
Right. When we are tearing through dense, hard steel, we can't have our table acting like a spring. We need an unyielding force.
And if air is a spring, hydraulic oil is a rock.
A liquid rock.
Essentially, yes. Hydraulic systems use liquid oil to drive their clamping pistons. And under normal machine conditions, liquid oil is virtually incompressible.
Right. There's no space between the molecules like with a gas.
Exactly. When you fill a hydraulic cylinder with oil and seal the valve, that piston is locked in place. It provides massive, rigid, absolute clamping force.
And the engineering manuals make it abundantly clear that this rock-solid rigidity is mandatory for heavy roughing and steel machining, because cutting steel is not a smooth, continuous peeling action.
Not at all. It's violent. Heavy roughing creates sudden, massive torque peaks. You frequently deal with interrupted cuts.
I read about that. That's when the tool hits empty space, right?
Yeah. Imagine a cutting tool shaving off metal, hitting an empty gap in the material's geometry, and then slamming back into a solid wall of steel at high speed over and over again. These are literal tool strikes.
Oh, wow.
And the shock waves generated by those impacts travel straight through the workpiece and directly into the rotary table.
And the tolerance for movement during these shock waves is practically microscopic. For precision aerospace or automotive work, The allowable displacement, like the absolute maximum amount the table is allowed to shift under load, might need to stay below 0.0003 millimeters.
Right. And to contextualize that, an average human hair is roughly 0.07 millimeters thick.
That is insane.
So 0.003 millimeters is a tiny, tiny fraction of a single hair's width. Only the incompressibility of hydraulic clamping can guarantee that level of absolute stillness under massive kinetic impacts.
I'm stuck on one specific detail from the mechanics section, though. The sources talk about the effect of gravity on the workpiece during steel machining.
Oh, this is a great point.
Wait, these are industrial vertical machining centers. They weigh tons. They have motors with massive horsepower. Why would the simple gravity of a workpiece even matter here?
It seems completely counterintuitive until you map out the geometry of a fourth-axis setup.
Okay, paint a picture for me.
Imagine a large, dense steel part clamped to the rotary table. That table is mounted vertically on the bed, meaning your heavy steel part is essentially sticking out horizontally into empty space.
Right.
Gravity is pulling down on the far, unsupported end of that part.
So it creates a lever arm, like holding a 20-pound dumbbell straight out at arm's length. Your shoulder feels a massive twisting force just keeping it level, even if you aren't doing any other work.
Exactly. Now add the cutting forces to that lever. Let's say you are doing vertical face milling or machining a large flange on heavy cast iron. The cutting tool is driving downward with hundreds of pounds of force. Gravity is pulling the offset weight downward.
So everything is conspiring to pull that part down.
Right. And if you're relying on a compressible cushion of air to resist the combined twisting torque of an offset iron casting plus an industrial cutter, the air will squish, the part will sag.
Which introduces indexing drift, where the table slowly slips out of its programmed alignment.
And you risk destroying the internal positioning mechanisms. To prevent this, heavy-duty hydraulic tables are often paired with a hearth coupling or a gear lock.
Okay, let's define a hearth coupling, because the manufacturer specs highlight this as like the ultimate armor for a rotary table.
So inside the table, there is a worm gear. This is a threaded screw turning a toothed wheel. It's brilliant for precise positioning, but it's fundamentally fragile if you hit it backward. You really don't want the force of the cutting tool impacting the delicate teeth of the worm gear.
Right, so the hearth coupling acts as a shield.
Exactly. Picture two thick steel rings facing each other. The face of each ring is machined with deep interlocking zigzag teeth.
Like gears on a bicycle. Similar, but facing flat against each other. When the table needs to lock, hydraulic pressure slams these two rings together, mashing the teeth into a single, unmovable block of steel.
Oh, got it.
The massive forces of the cutting tool are absorbed by these heavy interlocking teeth, bypassing the delicate worm gear entirely.
That mechanical locking chain totally protects the table and extends its life. The manuals also note hydraulic clamping is crucial for automated CNC cycles. If a robotic arm is loading a 200-pound piece of cast iron into a machine, manual clamping isn't an option, and pneumatic clamping just doesn't offer the necessary force guarantee.
You need the absolute certainty of hydraulic pressure.
But given all of these advantages, the rock-solid rigidity, the sub-hairline accuracy, the protection of the internal gears, you might assume manufacturers would simply use hydraulics for absolutely every machine they build.
I mean, it sounds like the obvious choice.
Right, I was wondering the exact same thing. Why even mess with air if oil is the ultimate unyielding force?
The answer lies in the ultimate enemy of mass production. Cycle time. Speed. Speed. The performance specs break this down, and the difference in response time is pretty stark. Pneumatic systems are lightning fast. Compressed air is a very thin gas with incredibly low flow resistance.
Yes.
When a signal is sent, that air travels through the pipeline structures almost instantly. The pneumatic solenoid valves switch in less than 0.1 seconds.
And the total mechanical action to fully clamp or unclank the table with air takes less than 0.5 seconds.
Meanwhile, the hydraulic systems are significantly slower. They usually take anywhere between 0.5 and 2 seconds just to engage. I want to look closely at the fluid dynamics here because oil is thick. It's viscous.
Very viscous.
The hydraulic pump actually needs time to build up that massive pressure. The thick oil has to physically push its way through the pipes, and that response time is heavily affected by the physical length of the pipeline, the specific viscosity of the oil, and whether the oil is cold from sitting overnight.
It just takes physical time to move liquid rock.
This is the ultimate trade-off in the system design speed versus holding power. But I'm looking at these numbers, though. Half a second for air, maybe 1.5 seconds for oil. Here's where it gets really interesting. We are talking about a difference of maybe 1 or 1.5 seconds. Does that really matter? Because as an outsider, 1 second feels like a rounding error.
I know, 1 second means absolutely nothing if you are making a single custom prototype in your garage. But industrial manufacturing is driven by scale. To understand why that second matters, consider a production strategy called equal division machining.
Okay.
Let's revisit that small aluminum valve body we discussed earlier. The VMC needs to drill a series of holes on all four sides of the valve.
Okay, so map out the sequence for me.
The machine indexes the table 90 degrees. Clamp. Drill. Unclamp. Index another 90 degrees. Clamp. Drill. Unclamp. It does this for all four sides.
Right.
That requires 4 separate clamping actions and 4 separate unclamping actions just to finish one single part.
Oh, I see. So if you are using hydraulic oil instead of air, you lose at least 1 extra second on every single clamp and unclamp. That's 8 seconds of dead time added to a single part.
8 seconds. Now multiply that across a real-world production quota. What if that single machine is tasked with churning out 2,000 of those aluminum valve bodies a day?
Oh, wow. 8 seconds lost per part multiplied by 2,000 parts equals 16,000 seconds.
That's nearly 4.5 hours.
That is wild. Over 4 hours of production rhythm completely evaporated.
Evaporated. 4 hours where the cutting spindle is doing absolutely nothing but hovering in midair, waiting for hydraulic oil pressure to slowly build up inside a cylinder.
4 hours of dead spindle time on a machine that might cost $500,000 is a catastrophic financial loss. It destroys your margins.
And this dictates the engineering choice. If the cutting forces are low, like drilling small holes in an aluminum valve, you absolutely prioritize speed. You want the 0.5-second pneumatic lock.
Because you don't need the unyielding force of oil, so you don't pay the time penalty for it.
Right. But if you are milling heavy steel with interrupted cuts, you gladly sacrifice those 4 hours of speed. Because trying to save time with a pneumatic lock would result in severe chatter, shattered carbide cutters, and 2,000 ruined steel parts.
So you match the clamping tool to the specific reality of the job.
Exactly.
But, mapping out production time assumes the machines are actually running perfectly. And anyone who has spent time on a shop floor knows that's a really dangerous assumption.
Oh. Speed and clamping force become completely irrelevant the moment the system starts breaking down. And these systems operate in brutal, real-world environments filled with microscopic contaminants.
Let's pull from the maintenance logs to look at hydraulic failures first. Because the obvious enemy of a system full of highly pressurized oil is leakage.
Leakage is the bane of hydraulics.
And the logs separate this into two categories. External leaks are highly visible, oil pooling around pipe joints, weeping from valve blocks, or just dripping down the side of the machine.
Right. And external leaks create immediate environmental and safety hazards. A puddle of hydraulic oil on the floor is a severe slip and fall risk for operators.
Huge liability.
Worse, if high-pressure oil mist sprays out near hot cutting tools or glowing chips of steel, you have a very real fire risk inside the enclosure.
But the maintenance manuals note that the true nightmare for an engineer isn't the oil on the floor, it's the internal leak, the hidden killer.
Because how do you diagnose a failing system if everything looks perfectly clean on the outside? With an internal leak, the pressurized oil is slipping backward past worn rubber seals inside the internal cylinder.
So the machine's computer reads that the valve is closed. It assumes the table is fully clamped with massive force. It sends the green light to the spindle to start tearing into the steel.
But the internal clamping force is slowly, silently dropping. Maybe the hydraulic brake is only holding its 70% capacity.
Oh.
The operator starts pulling finished parts off the line, scratching their head, trying to figure out why the surface finish is suddenly terrible, or why the indexing repeatability has wandered off by 0.05 of a millimeter. The brake is slipping, but there's no visible evidence of a leak.
And the logs show these internal leaks are usually caused by long-term seal aging, microscopic scratches on the cylinder walls, running the oil at too high of a temperature, or simply running dirty oil.
And the industry takes dirty oil incredibly seriously. Maintenance techs relying on ISO 4406 standards to monitor hydraulic fluid health.
Yeah, I looked into the ISO 4406 standard. It isn't just about looking to see if the oil is dark or foamy. It's a rigorous standard for counting microscopic particles suspended in the fluid.
Right.
They take a milliliter of oil and count exactly how many particles are larger than 4 micrometers, 6 micrometers, and 14 micrometers. They are looking for microscopic grains of metal or sand that act like liquid sandpaper, slowly scoring the internal walls of the cylinder until the pressure bleeds away.
Fixing a hydraulic system that has been compromised by particulate matter isn't a simple tweak either. It requires halting production, pulling the heavy table apart, replacing precision seals, flushing the fluid lines, and conducting rigorous pressure tests.
Sounds like a heavy maintenance
It
burden.
is a massive headache.
But, pneumatic systems are not immune to failure. They have their own hidden killer. And it isn't fluid leaking out, it's fluid getting in. The primary enemy of a pneumatic clamping system is water.
Which often surprises people who assume compressed air is totally dry.
Right. But ambient shop air naturally carries humidity. When an industrial compressor squeezes that ambient air down to 8 bar of pressure, it forces the water vapor to condense into liquid. You are essentially squeezing the humidity out of the air like wringing out a wet sponge.
Exactly. And if the shop's infrastructure, the heavy-duty air dryers, the particulate filters, or the oil-water separators, fails to catch that moisture, liquid condensation collects deep inside the pneumatic pipelines, the cylinders, and the solenoid valves.
And water inside high-precision pneumatic mechanics is disastrous.
The moisture aggressively attacks the system. It causes internal rust on steel components, and more critically, it physically washes away the micro-oil mist that is supposed to be lubricating the pneumatic seals.
The manuals highlight the failure of valve spools as a primary symptom here. A valve spool is the precision-machined metal cylinder that slides back and forth inside the valve body to direct the airflow.
Right.
When the water washes away the lubrication, that metal spool starts to drag. It rubs, it galls, and eventually it sticks. The cylinder moves slowly, and the table's clamping action becomes sluggish and completely unreliable.
And here is an incredible detail pulled from the winter maintenance logs of facilities in colder climates, in low-temperature shops, that accumulated condensation can literally freeze solid inside the pneumatic airlines.
Wait, really? It freezes?
It freezes solid.
I can just picture a maintenance technician pulling their hair out trying to troubleshoot that. Like, the rotary table is moving slowly or entirely failing to lock. They look at the symptoms and assume the heavy mechanical gears inside the table are shattered. They might spend hours tearing apart the machine, misdiagnosing it as a catastrophic mechanical failure. And the real root cause is just an ice cube blocking a 1/4-inch plastic air hose.
It is a shockingly common occurrence. This is why pneumatic systems require rigorous, unyielding daily maintenance.
Right, daily drainage routines.
Yes, technicians have to manage daily drainage routines, inspect automatic drain traps, monitor aftercoolers, and constantly test air quality. Providing stable, perfectly dry air to a pneumatic lock requires just as much vigilance as maintaining clean, pressurized oil for a hydraulic clamp.
If I can synthesize the maintenance philosophies we've just covered. With hydraulic clamping, the catastrophic failure happens when your working fluid escapes its boundaries. The system fails through loss of containment, but with pneumatic locking, the catastrophic failure happens when an outside fluid water invades the boundaries.
Yeah.
The system fails through a lack of exclusion.
Containment versus exclusion. That perfectly frames the daily battle maintenance team's fight on the shop floor.
So as we wrap up this deep dive into the engineering manuals, let's distill the core takeaways for you listening. If your production demands fast, light indexing drilling aluminum, making quick cuts, prioritizing blistering cycle times over heavy rigidity pneumatic locking is the engineered solution.
It minimizes your dead time.
Exactly. But if you are tearing into heavy steel, battling interrupted cuts and chaotic shockwaves, you absolutely require the unyielding force of hydraulic clamping. The optimal choice is always a calculated balance of cutting force, workpiece weight, rigidity needs, cycle time, and what your specific maintenance team is actually capable of supporting.
It is an exercise in ruthless optimization. You have to clearly define what your system needs to survive before you ever make the first cut.
And that framework of optimization extends far beyond a machine shop. We all deal with engineering trade-offs in the workflows and systems we design for ourselves every day.
Oh, absolutely.
We build systems to manage our time, our data, our projects. So are the systems you rely on built like pneumatic clamps, lightweight, highly responsive, and optimized for lightning-fast repetition? Or are they built like hydraulic systems, slower to deploy, heavier to maintain, but engineered to withstand chaotic, heavy impacts without breaking? You rarely get both.
You have to understand the specific forces your system will endure because, as the physics of industrial machining show us, you can never optimize for everything at once.
Well said. And I want to leave you with one final thought to sort of mull over today. Consider the sheer physics of fluid dynamics we talked about. Think about how these invisible, often ignored fluids, a burst of compressed air or a steady flow of thick oil, are the actual unseen muscles holding our modern precision machine world together. What other invisible forces are quietly holding your own daily systems in place? Think about it.